I'm going to invite the last speaker of this morning section. Is Mohammed Mustafa. The title is A Mixture of Two Gender Classification Experts. His co-workers is Eldin from Ain Shams University, which also another co-author is Eiji Mahdi, and himself is from American University in Cairo.
Hey, good morning, everyone. My name is Mohammed Mustafa. I'm presenting the work of mixture of two gender classification experts. And this is the work of my student, Yumna, and is in cooperation with my colleague, Professor Hani Mahdi. So I will follow the traditional menu as expected. So let's start with some motivation about the problem. So we are concerned here about the gender classification from facial images. This belongs to the family of problems that related to the 2D facial analysis. So what else can we do with the facial analysis? Of course, we can do face detection. We can detect the face from the images, and this is very useful. And it's a pretty standard feature right now on most of the digital cameras, as you can see. And it's useful to adjust the focal length of the camera. We can do identification. We can recognize the person on the image. And this is useful to organize our photo book. And of course, it can use for access controls and other usage for face recognition. We can do some expression recognition to understand what's the status of the person who is standing in front of the camera, like is he happy, angry, so on. And we can do these three steps, which is categorized as what we call the demographic classification. So we can start to understand what's the gender of the person, the ethnicity background, and some estimation of the age. So what gender classification is used for? What is it really useful, or we are wasting our time? So generally, gender classification is very useful for face recognition, because what you are doing in face recognition or identification, you have a database list of enrolled people, and an incoming person is standing in front of the camera, and he or she wants to get access to the room or building or whatever. So you take this picture and start to compare it against the enrolled people. So if you know a priori the gender of the person, and of course you know the gender of the enrolled people, so you can save time by comparing the incoming person to only the people of the same gender. So that, theoretically speaking, will save 50% of the search time, because you don't have to look at the other gender images. And it's not only speeding up, but it's also enhancing some accuracy, because more matching or more comparisons you are doing, the higher the probability that you will make errors. So by lowering the number of matching comparisons, then you are lowering your false acceptance rate, a typical type of error in the identification problem. The other usage, of course, is to have a better human-computer interaction, or machine in general. So I personally was involved in a project here for a media company that want to analyze the feedback of the user on their advertisements. So in New York City, there is a very famous square called the Times Square in 42nd Street, and over there you have lots of big screens on the streets, and it displaying lots of advertisements. And along those screens, there are some cameras that are recording the people who are standing in front of the screens and watching the advertisement. And they want to analyze the feedback of the watchers, the people who watch the advertisement. So if, for example, they notice that most of the people who like this advertisement are, for example, female, then the next version of the advertisement will have some pink background and so on. If it's men, then you have to have some fighting involved and so on. So related work in this field for the gender classification are basically divided into two categories. The first one is shape-based, where people rely on the shape of the face. Again, we are relying only the facial area. So, for example, Zhang was relying on the contours of the face and the facial features, and he reported some good result based on the contour of the face and the profile, and actually he added also the ear shape as well. Another work by Chow, he was relying on the actual landmarks constellation, like what's the ratio of the distance between the tip of the nose to the eye corner and so on, and produced some also results. But still, it's not the challenge here in the shape-based approach is that it's some kind hard in the first place to find these contours accurately or these landmarks accurately, especially if you are talking about uncontrolled conditions, like taking pictures in the sun where half of the face is lit and the other in dark and so on. So the other approach is the texture-based, relying on the actual texture of the skin. And there was the powerful work of McKinnon et al. And actually in this work, he was presenting at the beginning kind of survey of comparison between the gender classification methods. And they added also some combination of different methods, and they produced better results. So they have proven that by combining some of the already existing gender classifier outputs by an arithmetic method, they can get some enhancement in the accuracy. Another texture-based approach work by Robinson from the UK. He used what he called the single kernel conditional density estimation to not only estimate the gender, but he was estimating other factors as well, like the expression and the age class and some other demographic parameters. And he was testing on many databases. Unfortunately, most of them are private. The Ferret is the only one public database that he used to test on, and his overall accuracy was, correct accuracy was 77%. So we found out that there is some room for improvement here, mainly because most people were either testing on very controlled condition databases like the Ferret database. If you are familiar with it, that's a database that was captured in the United States for testing face recognition vendors' performance, and it was captured in controlled indoors environment in controlled conditions. So we found out that we can enhance some of the result that has been published by considering a mixture of multiple experts. So here we are considering 4 individual experts or classifier for gender, and we are considering the combination of those methods. So the classifier or the expert that we are considering, the least square support vector machine, that's a pretty well-known classifier. The single kernel conditional density estimation proposed by Robinson, the convolutional neural network, and the ADA boost in general, which use a threshold to classify whether it's the male or female. So I think the SVM and ADA boost are pretty much popular. I will go briefly over the other two approaches so you can be familiar with it. So the single kernel conditional density estimation proposed by Robinson, it's very easy. It considers the image pixels as a vector, and it's concatenate to it the list of features that you know. So now in the training phase, you have images of, for example, male, and you know the age group of this person, and you know the expression, smiling or whatever, and you give some numeric value to each one of these. So the male, you give a confidence on how do you rate this image as a male. For example, I'm confident 90% that this image is for a male. Expression, this person is smiling with a probability 95%, and so on. So this is the set of parameters which he called the x1, so this is the attribute vector, and x2 are the normal pixel grayscale values. And he concatenated this into one long vector and composed his training set like this. And then when I'm giving a new image that I don't know the gender or the expression of it, I have only the pixels. So I have only the x2 part. I don't know the x1, so I can estimate it by this estimation formula. It's pretty easy one. Everything here is unknown. x2 is the pixels of the image. The other parameters are some estimated values according to Gaussian density based from the training images. You can definitely go to their paper to see the exact, the more details on it. The other approach, the convolutional neural network, is not new. It has been used maybe 20 years ago for optical character recognition, and it was producing very good results. And so far, it's still the most accurate one used for optical character recognition in the United States Postal Office system in order to understand the zip code of the numbers. So it basically tried to downsample the input image at different resolutions until it finally has at the end an output layer of the number of classes. In our case here, we have two classes, male or female, and it has been fully trained using supervised method. So we are considering, as we said, mixture of experts. So we want to mix more than one of these classification methods. So generally speaking, a mixture of experts that you combine them. So the idea is how you combine them such that you get a better result of the mixture, better than any one individual expert. So we have tried the very simple mixture using the naive Bayesian approach. Our idea was to make something that will work in real time. So we opted for simplicity. So we started with a simple naive Bayesian approach, which is, as you all know, it's implemented by this simple formula to calculate the posterior probability, which will be your estimation of the class. It depends on the prior and the likelihood. That's something that you build by training. So how we do the training? So of course you get a set of images where you know the gender already, and the prior will be the accuracy of each individual expert by itself, and the likelihood of the confidence for each expert by itself. I can have, I know the probability of each of confidence value that this classifier is producing. For example, the confidence value of 5 was, it has a probability of 0.5. The confidence of 0.8 has a probability, for example, of 0.02, and so on. It has been seen this many times on the training images. So how we do the merge? So each trained classifier is, as we said, is trained alone on the set of images, and each one, it returns an output. Output means like a decision, whether it's a male or a female, along with a confidence. How confident is this classifier in his or her decision? We retrieve the prior of each expert, as we said, as we know already how accurate is each individual expert on the training set. Of course, according to Bayes, the prior has to be normalized to 1. So we normalize them such that the sum of the priors to be 1 in order not to violate the Bayesian rule. We retrieve the likelihood. We have stored the likelihood of each expert. And then we can calculate the posterior, as simple as using the Bayesian rule. And the final decision will be of the expert with the highest posterior. We are considering here only mixing 2 of them, again for simplicity. But in practical, we can do more than this. A quick numerical example, make sure that everybody understands the idea. So here, for example, if you want to merge these 2 experts, the first one, actually both of them are EDA boost, but the first one was trained on Gabor features extracted from the images, the other one from the hard-like features extracted from the images. For example, this image is coming from the ferret data set, and it has been normalized to 16 by 16, knowing the eye position. So the first classifier, or the first expert, it has a prior of 0.905. That means that it was 90.5% accurate on the training data set. The decision here was a female from this classifier, and the confidence was 2.5. This confidence is only relevant to each classifier alone. The likelihood of this confidence is 0.0217. Where did I get this number from? It's from the, this is the likelihood that I have stored for this classifier. And the same for the second one. It has a prior of 0.9363, and the decision was male, the confidence was this value, and the likelihood was this value. So if we apply our Bayesian rule, we normalize, as we said, the prior such that to have a sum of 1, and then we calculate the posterior of the first one, the posterior of the second one, and then we select the one with the highest posterior, which is the second one in this case. Then we will go with the decision of the second one, which was the male. So we have so many experts here. We have, as I mentioned, we were experimenting with 4 of them, and there are also many features to be extracted. As I said, we can do some Gabor feature extraction, hard features, or working on the raw pixel values. So there are many combinations to consider. So which one will produce the best value? We have actually tried most of the combinations, and we will go with combining the 2 experts that were making the different set of errors. So it doesn't make sense to combine 2 experts that were producing the same decision and making the same mistakes. So it doesn't make sense because they are basically close to each other. So it's better to combine 2 classifiers that were making like different mistakes. So So for example, here, these two classify the single kernel on the row pixel versus the SVM on the row pixel. They were producing 89% of the time the same decision, either correct or wrong, and 11 times where they have different, and those 11 times, 9% of the time the SVM was correct, and the other 2% the SK was correct. And for example, here, while combining these other two, they were producing the same decision only 70% of the time, and they were 30% of the time different. So here in this case, it's better to use to combine the other one because they were producing different results. So the other approach that, or the other ingredient that we have thrown in the mix was to try to enhance this merge by adding a third expert, but not at the Bayesian combination level, but at the output level. So it's like doing an arbitration. So if both classifiers, if both initial experts produce different results, then we will go to the third one. If the third one has high confidence, then we will go with his result. Otherwise, we will revert to the simple Bayesian classifier. So we call this the enhanced merging. So these are the set of data set that we have tried on. The ferret data set, that's a controlled data set, pretty much standard. The mixed DB, that's some of the images that we have collected privately to include different ethnic background people. The LFW, that's again the label face in the wild. It's a very famous database, and it has low quality and uncontrolled condition images. And the kin face, that's a pretty new database that we have noticed. It was collected from the internet. People trying to not to do gender here classification, but they were trying to do something else. But we have used it since we have seen some other people testing on it. So this is how we divided our data sets. We do, for the training, we have selected from each one this number of images, male versus female. We have tried to select the same number of male and female images. And train extra, that's to train the Bayesian classifier or the extra classifier. So this is to train each individual expert. This is to train the merge, and this is to test. And this is some results. The dark gray one, that's using single expert. This is the best individual one. And the light gray one is the merge using the Bayesian algorithm. And the enhanced merge using the Bayesian algorithm plus the arbitration additional expert that I mentioned. And it was convolutional neural network. So this was, the previous result was on the average on all data sets. That's individually on each of the data sets, at different resolution, 15 by 15, 24 by 24. This is some examples of the misclassified samples on the ferret and LFW. So here on the LFW, it's very clear that it's susceptible to some occlusion from the heavy sunglasses. So it's covering most of the features, or harsh lighting condition like the standing in the sun. This is the comparison with the McKinnon method. Again, he also was doing merge of different, but he was doing merge with a different method and different individual classifiers, but he was testing on the same data sets, so that's why we have produced our result comparison here with them. And this is LFW. So in conclusion, we have proposed a new technique to combine the mixture of experts for gender classification by two classifiers, and we can add a third expert. On the average, we have seen that the best individuals are the EDA boost on Aaaa featured and the SVM, and adding a neural network as an extra expert. For future work, we are currently doing tests with merging more than 2 different classifiers at the base level. And we are considering also some other features in addition to the Aaaa features and the Gabor features. And we are also considering adding some shape-based classifier to the mix. Maybe it will enhance our result. So, thank you.
Although we are a little bit over time, we have time for one question.
So I'll try to. I'll do 2 in 1. The first one is you showed results with 1 operational point in the curve, right? It would be interesting to see how the classifier performs when you have the full receiver operator characteristic curve. And when we see that, we can like better predict where to combine the classifiers, because when you showed the accuracy there, I'm not sure if it's better sensitivity or specificity or what's going on in this scenario. And the second one is a suggestion. You have tested individually on the data sets, and it would be very interesting if you can train in one data set and test in the others, because this is more like what's going to happen in reality, because you do not have certainty about what's going to happen and the sensor that's going to acquire the images and etc.
Okay, thank you. Okay, so for the first question, the reason, yeah, definitely reporting the full ROC will give better picture of the accuracy, but maybe we selected to do this in order to compare with the other previous work, because the previous people reported only a specific point, their best result. So, yeah, of course, yeah, but yeah, definitely we will consider this in the next version of the paper. For the second question, you were suggesting to train on all of them. Definitely, this is the training. Yeah, but training on one database only and testing on the other. Well, oh, okay. Yeah, that's something new, but again, at this case we cannot compare with the previous work because they were. Yeah, okay. Yeah, for reality, I was thinking of something else. I was thinking of doing the training once on a mixture of databases, and then we fix the training, and then we ship like a product, and it will work everywhere. So I think in this case, it's better to train on multiple data sets as a whole, one data set, training data set, and then forget about training after that. So that's what I would think. But again, for reporting comparative results with other people, that's why we've selected to train on each one individually. Thank you.
Okay. I'd like to know, in the tables with the results, you showed a normalization.
Yes.
I'd like to know what kind of normalization you're doing. Is it like in plane rotation fixing or something like that, or just the size of the image you are?
Well, yeah, in all the results that I've reported and others have reported, there were done some normalization regarding the size, because we were assuming that the face detection problem is solved already and we have the face, so we are using only the facial area. But here normalization, what we mean and what the other people meant by normalization was normalization on the grayscale level. Like enhancing the contrast or like histogram equalization or some other methods. So here with and without, and the same for other people with or without.
Okay, I'd like to thank you, not just Mohammed, but also all the 4 speakers this morning. Thank you.
Thank you.